Okay, now let's talk about next section, the section 3.4. Uniform continuity. So remember that when we define a continuity, we say that uh, we say a function from a domain to the set of real numbers, and you have a point in this domain. Then we say f is continuous at a if for all epsilon greater than 0 there exists a delta greater than 0 such that x minus a less than delta implies fx minus fa less than epsilon. This is our continuity at point A. And when we discuss this continuity, we actually emphasize this delta actually depend on what? Depend on this all the given information. So you see here, you have domain I, you have function f, you have epsilon, you have a. So this delta is a function of all those four factors. Whenever one factor changes, this delta may change. We only say may change. Okay? But let's check. Domain, function, they are together. Once you have a function, have a domain, so it's always fixed. So these two things we cannot change. We cannot change it. Whenever we have a function, we always have this the expression of function and the domain of function. So it is fixed technically. And this epsilon, of course, this epsilon will become smaller and smaller and smaller and smaller. So epsilon always changes. So delta must be a function of epsilon. In general, not always, not always. Okay, in general, this delta always must depend on the epsilon. If if the function is constant function, this delta does not depend on epsilon. But that's not interesting. Okay, so let me write down. If f is the constant function, then delta does not depend on epsilon, because if you have a constant function, this difference is always 0, because it's fx minus fa ops value is always 0. So it's a degenerate case. So we don't include this, or not include. We don't care this a lot. Okay, so delta always depend on epsilon. So the last factor becomes optional. So sometimes this delta depend on a, sometimes it does not depend on a. So okay, so there are two options. One case, this delta depends on a. The other case, the delta does not depend on a. Okay, so we are talking about not depending on a case. That is a uniform continuity. So definition 3.35. Okay, let E be a non-empty subset of R, and f from E to R a function, then f is said to be uniformly continues on E, if and only if for every epsilon greater than 0, there is a delta greater than 0 such that x minus a ops value less than delta, and a and e, x and a belong to E. This imply ops value fx minus fa less than epsilon. Okay, so here you see this ax, they are introduced after delta, so this delta does not depend on a or x. This delta only depend on, okay, this is a complete definition, so here we can see that this delta only depend on this domain E function f and epsilon. Okay, so it does not depend on A, does not depend on X. Whenever 2 points are close enough, here it's not 2 points. Whenever X is close enough to A, so there's a relation. A is a fixed, X is approaching A. Here, just say whenever, it doesn't matter where you have this pair of a point, whenever those 2 points are close enough, the values will be close enough. So this is a uniform continuity. Okay, so let's see the examples. So prove that fx equal to x squared is uniformly continuous on the interval 0, 1. Uniformly continuous on the interval 0, 1. Okay, now let's see the proof. Well, we're going to prove it's uniformly continuous. At least it's continuous. So, given epsilon greater than 0, we are going to study for xa in E in the 0, 1. We're going to study fx minus fa. fx is x squared. Fa is a squared. So we put ops value. X squared minus a squared is x minus a, x plus a. And this x minus a term, remember, you will keep it. X minus a term, you will keep it. X plus a can be considered as a coefficient. Sorry, x minus a. And then this part, we're going to use what? Use a triangle inequality. Ops value of x plus a is less than or equal to ops value of x plus ops value of a. Right? Okay, in this one, remember, x and a are both in the interval 0, 1. So ops value of x, ops value of a are both less than 1. So this quantity is less than 2. Right? So that's totally depend on this observation. It's less than 2. So given epsilon, with this analysis, choose delta be epsilon over 2. We choose delta be epsilon over 2. Whenever ups value of x minus a less than delta, whenever this quantity is less than delta, ups value of fx minus ups value of fx minus fa is going to be, you see here, less than 2 ups value x minus a less than 2 delta. Oh, this is, yes, less than 2 delta, which is epsilon. Okay, which is epsilon. Okay, then you see here this delta, it has nothing to do with a or x. That's why we call it uniform. Uniform in terms of a base point. There's no base point. Whenever 2 points are close enough, x and a, they are close enough, you always have this property. So fx is uniformly continuous on the interval 0, 1. Of course, uniform continuity implies continuity. This is a strong continuity, right? Remember that we have it. Okay, so from this example, we also see that this delta, it will depend on this 0, 1. This is already end. If we choose f from 0, 2 to r with fx equal to x squared, then you will see that this delta will be what? Ups value of x plus ups value of a, it will be less than or equal to 4, right? Because sum is less than 4. Each of them is less than 2. So delta will be selected as epsilon over 4 at least. Epsilon over 4. So this number 4 depends on this the domain. So delta is in general a function of a domain, a function of a function, and a function of a epsilon. Domain, function, and epsilon. Right? So also from here you can see that this fx, which is x squared, is uniformly continuous on any bounded domain. Any bounded domain. Why we need bounded? Because when you have bounded, then a boundedness, the ups value of x, ups value of a, will be less than or equal to some number. Then you just double that number. It's 2m, right? If you have a bounded domain, then the AB will be bounded by capital M. Then this is 2m. So this function is uniformly continuous over any bounded domain. But if it's unbounded, the situation will be different. Okay? It is okay? So let's see what happens if it is unbounded. Okay, show that fx, which is still x squared, is not uniformly continuous. On unbounded domain, on R, it's not uniformly continuous. Okay, let's see the proof. We're going to show it is not uniformly continuous. If you prove it directly, we have to say delta must be a function of a base point. You want to show something must be. So if we prove directly, we need to show that delta must be a function of a base point. Well, whenever you want to show something must be, it will be slightly difficult because you have to consider all possible situations. That is usually not very easy to handle, to cover, or to claim. So whenever you have some situation like this, possibly you can choose to prove it by contradiction. Okay, so whenever you have some condition like this, you want to show something must be, then you can prove it by contradiction. Okay, so suppose f is uniformly continuous. On R. F is uniformly continuous on R. Then for any epsilon greater than 0, there is a delta which is only a function of a domain F and epsilon, such that whenever x minus a less than delta, you have fx minus fa less than epsilon. So this is a definition. Okay, so here any epsilon, we just pick up one, or pick up one value. We can choose whatever value we like. To be simple, choose epsilon to be number 1. You can choose to be 10, a million, whatever. All the number will give you is contradiction. Okay, epsilon is equal to number 1, and there's a corresponding delta. There's a corresponding delta. Okay, so now let's see what is the situation. There you have x and a. The idea is the following. X is very close to a. For example, let x be a plus delta over 2. X be a plus delta over 2. So the difference, this is positive. Delta is always positive. So the difference is less than delta. So it's good. And x squared minus a squared. So a plus delta over 2 squared is a squared plus delta a plus delta squared over 4 minus a squared. So it becomes delta a plus delta squared over 4. Okay, so that's our computation. Like, how do we go to the next step based on the computation? Okay, delta will be small enough, sufficiently small. What, right? So we just choose small delta. When delta is small, delta squared over 4 is also small. So this is not a problem. This second factor is not a problem. The problem comes from the first factor. So delta is small, but the delta is still fixed. Delta is small. A can be as large as possible. A can be as large as possible because you have an unbounded domain. Can be as large as possible. So delta is fixed, A is large enough, so that delta times A will be greater than 1. Why we choose 1? Because here we choose 1. Okay? It will be very large. The difference will be not less than epsilon. Okay, so this is an idea or the reason we go through the next proof. Here. This is all the analysis. You will not see this in the formal proof. You just have it in your scratch paper. Okay, so epsilon equal to 1, there's a corresponding delta. When you have a delta by the Archimedean principle, there is an n in the set of natural numbers, so that n times delta is greater than 1. N times delta is greater than 1. Okay, a very large n. Then choose A be this n and x be n plus delta over 2, like this. Then we have, okay, so epsilon should be greater than ops value of fx minus fa. This is ops value of x squared minus a squared, like here. And it is equal to this delta a plus delta squared over 4. They are both positives. You don't need the ops value. Delta is a positive square. Square is still positive. Over 4 is positive. Delta times a is, where's delta times a is greater than 1. So you get contradiction. It's a contradiction. So contradiction. Sometimes you see this type of a symbol. Okay, so this is a contradiction. Therefore, f is not uniformly continuous. Over R. Over R is too large. It's too large, so the function is not uniformly continuous. If it's bounded, then it's always uniformly continuous. But if it's unbounded, because of this A can be chosen as large value as possible. So it makes this n times A times delta extremely large. Okay, so this is an example of a non-uniform continuous function. This comes from the unboundedness of the domain. So we have a continuous function, uniform continuous function. We know that uniform continuous function just means this delta does not depend on the choice of A. Why is it important? Why is it important? So the thing is here. Okay, let's finish the proof. So fx equal to 1 over x is continuous. Over 0, 1. Over 0, 1. But fx, which is fx is not uniformly continuous. Uniformly continuous over 0, 1. Okay, so it is continuous but not uniformly continuous. You can try to see why it is not uniformly continuous. You again prove it by contradiction. If it is uniformly continuous, then some strange situation will happen. You possibly will choose 1 over n stuff. Try to do it. It's not difficult. It's very close to this square, but you have to flip it. Okay. Then let's see this. If we have a sequence xn is equal to 1 over n. This sequence is a Cauchy sequence. In 0, 1. It's just a Cauchy sequence. We don't say it has the limit is in the domain. If the limit is always in the domain, that's closed domain. Here it's open. So itself is a Cauchy sequence. Cauchy sequence will have a limit in the set of R. Okay, so you have a Cauchy sequence, but fxn, the continuous image of a Cauchy sequence, is not a Cauchy sequence. In R. So it means the continuity does not preserve the property of a Cauchy sequence. Okay, so Cauchy sequence is a nice property. Unfortunately, the continuity, simple continuity, cannot preserve the Cauchy sequence. So that's bad. Well, we can see that the uniform continuity will preserve the property of Cauchy sequence. So that's one of the important reasons we introduce a uniform continuity. Suppose that E in R and f from E to R is uniformly continuous. Okay. If xn in E is Cauchy, then fxn in R is Cauchy. Okay, so it just means uniform continuity will preserve the property of the Cauchy sequence. Well, we're going to show that the new sequence is a Cauchy sequence for every epsilon. There is a capital N such that whenever n and m greater than capital N, xn minus xm ops value is less than epsilon, right? So given epsilon greater than 0, you have an epsilon. We are looking for capital N. But here f is a uniform continuous function. There is a delta greater than 0 such that for x minus a less than delta, such that x minus a less than delta implies fx minus fa less than epsilon. The reason we use delta is that this epsilon corresponds to the value f. Delta corresponds to the input x. Okay, so they have different target. So epsilon can only be applied to fx, fa. Delta is directly applied to x and a. Okay, so epsilon. From epsilon, you have this delta. X minus a less than delta implies fx minus fa less than epsilon. Then for this delta, there is in capital N in the set of natural numbers such that for all n m greater than or equal to capital N, ops value f xn minus xm is less than delta. This is the property of the Cauchy sequence. Xn minus xm less than delta, then absolute value fxn minus fxm less than epsilon. This is a uniform continuity. Okay, right? So we just apply those two definitions directly. Then let's collect the information we have. Given epsilon greater than 0, there is a capital N in the set of natural numbers such that whenever nm greater than capital N, fxn minus fxm absolute value less than epsilon. What this is by definition a Cauchy sequence. So fxn is Cauchy sequence. Okay, so that's the one of a key difference between the continuity and the uniform continuity. All right, continuity and the uniform continuity. Okay, so they are very close. The only difference is the dependence or independence of the base point A, but simply with that difference, we see this important application or connection between those properties with those two definitions with Cauchy sequence. So they are so different, but if we restrict our domain, if we have some nice domain function we cannot modify. If you modify function, of course, it's not interesting. You're dealing with different function. There's no common thing we can discuss, but we can modify the domain. So the next theorem tells us if we have some nice domain for the same function, you will have some different property. Suppose that I is a closed bounded interval. I is a closed bounded interval. If f from I to R is continuous, on I, then f is uniformly continuous. Okay, so this is a theorem. We're going to prove it. Well, actually, you see here, closed bounded. If you study a little bit topology, we know that for R, any closed bounded interval is a compact set. Closed bounded sets in R are compact. Compact set means every open cover has finite subcover. Okay, so anyway, that's a topic in the topology. You may or may not see this. Okay, so if you have this concept in your mind, then this theorem can be written as the following. On compact set, continuity is equivalent to uniform continuity. Because here you see, from continuous function continuity, you get uniform continuity, but uniform continuity is automatically continuity. So these two concepts are equivalent. The important restriction is that you have to have a compact set. Okay, so later, whenever you see a closed bounded domain and you have a continuous function, you can automatically say this function is uniformly continuous. Okay, whenever you have a closed bounded domain and a continuous function over it, then this continuous function must be uniformly continuous. All right. Well, let's see how do we prove it. This is a remark. It's not a proof. Let's see how do we prove it. Again, you are going to show some uniform continuous. You will show that epsilon must not depend on point A. That's difficult. It's hard to cover. So we are going to prove it by contradiction. Suppose that f is not uniformly continuous on I. Okay, not uniformly continuous on I. Remember, it's still continuous, but not uniformly continuous. Not uniformly continuous. Continuous means for every epsilon there is a delta such that whenever x minus a less than a delta, fx minus fa is less than epsilon. Every epsilon. Okay, so every epsilon there exists a delta, x minus a less than delta, fx minus fa less than epsilon. This is the definition. Then the contrary is that there exists epsilon greater than 0 such that for all delta greater than 0, this is for all x minus a, then there exists xa with x minus a ups value less than delta, but fx minus fa greater than or equal to epsilon, right? That's the contrary. Okay, now let's see. So there exists epsilon. So there is an epsilon 0 greater than 0. And for every delta we're going to choose 1 over n. There's always a xn, yn in I with xn minus yn ups value less than 1 over n, but fxn minus fyn, the ups value is greater than or equal to epsilon 0 for all n. For all n. Okay. Well, we basically have two sequences, xn sequence and yn sequence. You have a bounded interval. Bounded interval means the sequences xn sequence, yn sequence are bounded. Bounded sequence by Bolzano-Weierstrass theorem, we know that they have convergent subsequence, right? They have convergent subsequence. Okay, so let's see, xn xn has a convergent subsequence. For example, let's call it xnk. Xn has a convergent subsequence, let's call it xnk. And then let's say the corresponding ynk is still bounded. You have to start from 1. You see, there's some orders. You must start from 1, you get the subsequence, and then you consider the corresponding subsequence from the second sequence, then this is still bounded, then by the same theorem, x and k has a convergent y and k has a convergent subsequence. Let's say it YNKL. YNKL. So you see here, you cannot directly say they are both bounded. Then by this theorem, xn has a convergent subsequence, yn has another convergent subsequence. If you say that, I don't know if they share the same subindex or not. Okay, maybe this xn is the x1, x2, x1, x3, x5, x7, x9 stuff, and the y is like y2, y4, y6, y8. So if that happens, then there's no argument about the intersection. How can I know they share the same index? But with this order, you see, you start from xn, you get x and k. You get the corresponding x and k, then you get y and kl. And y and kl converges. X and k converges. All its subsequences converges. So x and kl also converges. X and kl also converges. X and kl also converges. X n kl minus y n kl is less than upper value of 1 over n kl. Right? That's here. That's its property. Well, as L approaches infinity, this upper value will be 0. This implies the limit x n kl is equal to the limit y n kl. They share the same limit of those two convergent subsequences. They share the same limit. And this limit must belong to I, because I is closed. I is closed, so the limit of the convergent sequence must belong to this set. Let's call this x. This is y. But we know that fxn minus fyn is always greater than or equal to epsilon. Always greater than or equal to epsilon. So 0, epsilon 0. So even you pass it to the limit, here the limit is compatible with this. It's not a Cauchy sequence. There's no Cauchy sequence. So we get the limit, these two limits. It is still greater than or equal to epsilon 0, which is a contradiction. Because x is equal to y. Because x is equal to y, this is equal to 0. But it's greater than epsilon 0. It's a contradiction. So therefore, f must be uniformly continuous. It's because you assume it's not uniformly continuous, then you get this contradiction. So it has to be uniformly continuous. Okay? Okay, so we finished the proof of this important theorem. This theorem is one of a important property about compact set and a continuous function. All right, so far we introduced the uniform continuous function uniformly continuous function, and we see that there are serious difference between the regular continuous function and the uniformly continuous function. They're quite different, but we also unify them over the compact set. Over the compact set, there's no difference between the continuous function and the uniform continuous function. Okay, so that's it. Okay, so we finished this video and we're going to continue in the next video. Okay, thank you.